All right, so we are doing the 2017 HSC paper from Chemistry 33. Okay, so it's one of those equilibrium constant calculations again. The question says the contact process for the production of sulfuric acid includes a step whereby sulfuric dioxide or sulfur dioxide is converted to sulfur trioxide in an equilibrium reaction, and this is the reaction that we have. And that is our delta H, which means this is an exothermic reaction, which means heat is being produced on the product side. Okay, let's go to the very first question. It says, sketch a second curve on the same axis to demonstrate the production of sulfur trioxide over time when the reaction is repeated at a higher temperature. Clearly label the two curves. Well, what we know is if we increase temperature, we also increase the rate of reaction. So what I should see here is we should see on this curve, um, it peaks up a lot faster than the original curve. But this is an exothermic reaction. So by increasing temperature, what I'm actually doing is I am driving this reaction towards the left. So it's favoring an endothermic reaction. Okay, so increased temperature always favors the endothermic reaction. In this case, the reverse. So my overall concentration of SO3 will be less. So if I draw it out, I'm going to see a sudden increase. So that increase is going to be higher, but that plateau point is reached earlier, and the overall concentration is less. I'm going to graph it, and then I'm going to say due to increase in temperature, and I'm also going to label the original one original. Okay, so that's basically it for that question. Then the next one we look into is this one here. So it says at a certain temperature, the equilibrium constant is 12.1. So we know what that is. Might as well just write it down on the side. At the same temperature, we have that many moles of sulfur dioxide, we have that many moles of oxygen. We're added in 1 liter, and at a point in time, so at a point in time, the concentration was measured as this. So we have some initial concentrations, and we also have some equilibrium reached concentrations as well. So have we reached equilibrium? If we reached equilibrium, that means that our value that we're looking at is Q needs to be equal to K. So we need to check that out. Okay, let's try and set things out. We need to write the chemical equation. Luckily for us, it's actually written at the very top of this page already. So sulfur dioxide, half oxygen and trioxide. So sulfur dioxide plus half of oxygen gas, and then we get sulfur trioxide. Gas, 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 like that. Okay, so that's what we see. Now, the next thing we need to know is what is the concentrations of each one of them, because without these, I can't actually use the ice table. So I'm going to try and find the concentrations first, which luckily for us, the concentration here is 1 mole over 1 for both of them. So the concentration of sulfur dioxide is 1 mole per liter, and the concentration for O2 is also 1 mole per liter. So, easy stuff there. Okay, I'm going to create some space. What I'm going to do now is going to draw up my ice table. So SO2, O2, and then SO3. Okay, so just write down what we have. We have that the initial concentration, okay, the initial concentration was 1 mole there and 1 mole there. We find that at the end of this, the end concentration for sulfur trioxide, okay, is 0.7 moles molarity, okay? So, what have they lost? Well, OH is, or O7, that's plus X. So plus X is equal to that, okay? The sulfur dioxide is in the same coefficient ratio, so 1 to 1. So it has lost, in this case, 0.7. So at the end, it has 0.3 moles per liter. The next one we have is the O2. Okay, so the oxygen coefficient is half and sulfur trioxide is 1. So this, the sulfur trioxide, is twice the amount of the oxygen, so twice the amount of it. So it's losing 2x, which is 2 times 0.7. So also make sure it's negative. Okay. All right, let's just change that a little bit. I did a little error, so it shouldn't be times by 2. So it's actually half the amount. So if it's half the amount, it would actually be 0.35 that we've lost. 0.35 we've lost. And if I put it into my calculator, I'm left with 0.65. Okay, all I need to do now is plug it into my equilibrium constant equation. So sulfur trioxide on top, and then the sulfur dioxide and oxygen at the bottom. And I get 3.59. So this is the reaction quotient we found. The concentration ratios at a particular point in time. If we want to know if we've reached equilibrium, let's just put K here, K and Q. So we know that K is 2.1 and Q is, if we just round it off to 3 sig figs for our own convenience here, 3.59. So it's smaller than 12. So Q in this reaction is smaller than K, which means not at equilibrium. Reaction is favoring the reverse direction. And so that is the direction with sulfur dioxide and oxygen. All right, besides that little hiccup I'd had with the halving there, that's exactly how you do the question.